Get to pick. What questions do you guys want to do? Nine. Yeah, the matching the picture one. This one. So this is the very last one on the back. I moved it in above the tree, the second one, the top. Left. Yep, right up one. That one. Yep. All right. So what we're looking at here is we've got a bunch of different parabolas. Yes, I know their arrows are weird because Google Docs is a jerk. And we've got a bunch of different functions down below. So what we're going to do is we're going to play match 'em up. So if I look down here at this first equation, what we're going to do is we're going to think about our transformation form, that ax minus h plus k guy. And we're going to notice that all of these equations use 2's and 1's. So it's all about those h and k values. There's no a changes here. We don't have any reflections. We don't have any stretch or any compress. It's just the shifts. So looking over here at Q, what is our h value? 2. What is k? -1. What does that mean transformation-wise? Right 2 and down 1. So we're going to look at our pictures and figure out which one has gone from the middle. The middle is here. I'm just going to mark it on all of them because I know it's sometimes hard to see. Which one has gone right 2 and down 1 from that origin? D. It went right 2, down 1. It's right there. Let's look at S, the one right below it. What is our h value here? -2. What is our k value? -1. Thank you, dear. So what does that mean happened transformations-wise? Yep, left 2, down 1. So which of these went left 2 and down 1? B. Okay, so that's the vibe with these. This one went left 2, down 1. That's the vibe with these. These last two I want you to do on your own. I want you to practice this. Doing it without holding your hand through it. So find your H, find your K. What does that mean transformation-wise? Match them up. Okay, what else do you guys want to work through? 8. It's a very similar vibe. Very similar vibe. So we've got here, it's kind of an error evaluation thing. But the way we're going to work on it is we are going to identify all the pieces. We're going to write our own equation and use that to kind of help spot where she made mistakes. I think that's the easier way to do it. I'm going to ignore it. If I was working on this on paper, I will sometimes grab a Post-it note, which I can always give you, and put it here because I don't want to see hers right now. I want to do my own first. So Kayla remembers that the parent function is the absolute value of x because it's a V shape, so it's an absolute value. She says this graph has gone 2 units left and 1 unit up and has been reflected. She's right. It did go 2 left, 1 up, and it's been reflected. What does that mean our values are going to be? We need A, H, and K. A is going to be negative. And since we don't have any stretch or compress, I'm never going to have you read a stretch or compress off of a graph. We're going to have -1. What do you mean? Why do we have -1? Because we know it's negative because it's been reflected. And I will never, ever, ever have you read a stretch or compress. So 1 is kind of the default state. How about H? -2. Okay? 1. That tells me reflected, left 2, up 1. We have all the pieces. So when we write our transformation form, think through our generic A, x minus h plus k. We're going to plug in our pieces. -1 times the absolute value of x minus -2. Minus -2 becomes +2 plus k. So I do not start, when I'm doing these, personal preference, I do not start with looking at her equation and trying to mix and match. It'll make things in my head fuzzy. I start with writing my own equation and then comparing my work. So what mistakes did she make? She forgot that it's x minus h. So she made a mistake there. Did she make any other mistakes? She doesn't have that negative value out front. So she made 2 mistakes here. So find the right equation and then check it. The teachers always write the answer key before we start looking at your work. Okay? What else do you guys want to go through? Number one. So we're looking at this graph, we're reading a bunch of pieces off of it. So first things first, is this linear or nonlinear? How can we tell? It's not a line. Is it a 1-to-1 function? What do we think? First things first, is it a function? Yes. Is it 1-to-1? No. So we're not always going to ask you the is it a function question first. You have to think that first. So function is the vertical line test, which yes it is, absolutely is. It is not a 1-to-1 function. It fails that horizontal line test. My shoes are very squeaky today, and it's going to drive me nuts all day. All right. So then we're looking for our vertex, or our point where it bounces, a point where it changed direction. So where is that? And I know the grid is really hard to see on your paper, so I'll zoom it in up here. Where is our vertex? Yes, 3, 1. This guy. 3, comma, 1. It's the point where it bounces, that place where we moved it from. Is this a maximum or is it a minimum? Think about our extrema. It's a maximum because it's a little baby mountain. Okay? This is all some last chapter stuff, but we're working it into stuff we're doing now. What type of symmetry does this have? So you remember that? Line symmetry. Remember, line is that I can fold it. I could fold this parabola in half. You can have line symmetry, point symmetry, or no symmetry. All right, so then let's find our domain. Which x values work? I was like 2 does work, but so does 1, and so does 3, and so does 27, and so does -1. Yes, dear. 3 and 6 do work? Yeah, they do. I was going to say, there's not any particular ones that don't work for us, right? So it's absolutely fine to start with thinking individual values. Totally fine. Excellent strategy. Good way to get started. Give yourself something to look at. Then we look at, is there anything that doesn't work? No. I can use any number in the existence of the universe. So we could go from negative infinity to positive infinity. Or, again, 2 options. All real numbers. I do not care which way you write it. What's up? Behind the tree, second folder up. How about our range? So when we use those any real numbers, where does it land? Say it louder. Negative infinity and 1, right? So if we're doing it in our interval notation, it does go smallest to biggest. So the negative infinity is smaller. Let me get the right color. So negative infinity. And the very, very highest my y's go is 1. And since 1 counts, I can touch it. It's right there, and it's a valid point. We use our little square bracket. Or if we're doing it algebraically, we can say y is less than or equal to 1. I don't care if you write it this way or if you write it this way. You don't need to do both. Pick one. So then we're looking at end behavior. That describes our arrows. This is another last chapter thing. So we think about as x approaches negative infinity. These guys, this is end behavior. Then my y does what? Negative infinity. As my x gets real small, my y's are going down. So then we talked about when x gets real small, let's talk about when x gets real big. As x approaches positive infinity, my y's approach what? Negative infinity. Because the right arrow is also going down. So then our last piece here is kind of smushing it together with the matching up the u's on the backside. How did it move? How did it change? I see if we can find an equation that kind of works. So what transformations happened to this function away from the origin? Right 3. Up 1. Anything else? It's been reflected. which means, what's our h? If it moved right through, your h is what? Positive or negative? It's positive if it goes to the right. How about our k? 1. And what's our a? Negative 1. So we're going to look at our little equations down here and see if we can find something that works. The third one? Yeah, the third one looks good. We can also come through and cross stuff out. I know this one doesn't have a negative a value, so I know it's not that. This one also does not have a negative a value, so we can do that. And it limits the number of things we have. So find something you can eliminate. These two looking in here, we know that h was positive 3. This one has that positive 3 because it's x minus h. So we're just looking in there and trying to find the pieces we can. Any pieces we got. Number 2, yeah. What kind of function is this? So you can also come in here and kind of, again, use this as like a list. Is this a line? No. Is this an absolute value? Is it a v? No. Piecewise, maybe. Is it a step function? Does it have only horizontal steps and I can walk on it? No. So now we're looking at, is this piecewise or is this something we haven't seen before? What do we think? Piecewise. It's lines we've worked with, cut into chunks. So this is a piecewise function. Piecewise functions look like I took other functions, lines, chopped them up, and put them together like confetti. Is this function continuous? Is it discrete? Remember, continuous is one solid line. Discrete is freckles and scatter plot. So this is neither. What else do you guys want to do? 6. There's a lot in number 6. For number 6a, you don't have to put it in slope-intercept form first. That is a very easy way to do it if you get super duper stuck. But it's also doable as our x and y intercepts. So I will post the answer key for this later. I've done it both ways on my answer key. So what's your instinct on this? Yeah. I think that's the easy way when it's in standard form. So for when my y is 0, it covers this guy up. When y is 0, this term is away because 6 times 0 is 0. 3x minus 0, and we get 3x equals 12 for one of our intercepts. So what is my x-intercept? 4. 1, 2, 3, 4. We do the same process for my y-intercept. If my x is 0, this term disappears, and we get negative 6y equals 12. So what does y equal? Negative 2. Are we connecting these with a solid line or a dotted line? a dotted line because this inequality here does not have an equals to. So this is dotted. So when I connect them up, and when you use your ruler, we're gonna look something like that. That's the line part. We're not done yet. Because when we have inequalities, we need to have shading somewhere. We figure out where our shading goes by selecting a test point. Any point not on our line. So what's a point we can use? 0, 0. It's my favorite point to use if it's available. So we're going to test that in our inequality. 3 times 0. Minus. 6 times 0. And I want to know if that is greater than 12. So 3 times 0 is 0. Minus 6 times 0 is 0. 0 minus 0 is 0. Is 0 greater than 12? No. So that means this is not our solution side. So we're going to color the other side. Down here. So the test point shows us which side has our solution. We take the truth, we make it bright and bold and beautiful, make it bright and colorful. If you need highlighters for that, I always have them. All that jazz. It's a very similar vibe when we have it in slope-intercept form. When we have our slope-intercept form, we can just hop straight into the line because we already have all the details here. This, we're graphing y equals mx plus b. So where are we starting? Where's my first point going to be? At -3. This is my y-intercept. So 1, 2, 3, down here. How do I move? Up to right 1. Up to right 1. I'm going to go up to right 1. I'm going to do again, up to right 1. And again, up to right 1. And again, up to right 1. The more points you have, the easier it is to connect them up. Are we using a dotted line or a solid line here? Solid. How do we know? Because it's got the equals to. So we're going to do our very best. Y'all going to use a ruler. My line is super wonky. You're going to use a ruler. Those rulers in the boxes on the tables. And then we need to shade. So we're going to pick any point not on the line. 0, 0 is a fine choice because it's not on our line. So let's check it. We want to know if 0 is less than or equal to 2 times 0 minus 3. Is 0 less than or equal to 2 minus 0 is 0, 0 minus 3. Is 0 less than or equal to -3? No. I would rather be broke than owe somebody $3. Screen's being a jerk. There we go. There we go. Questions on the inequalities. Okay, let's do our absolute value. When we're doing our absolute value, I highly recommend we do the x plus h, y a plus k guy, if we have that show up, because it's easier and faster. If you want to guess and check, that's fine, but it is going to take you a lot longer. So I'm going to come in here and we're going to find out what is our, ooh, that's not a pen. What is our a value? -1. What is our h value? +2. What is our k value? 1. Yeah. And what we're going to do is we're going to take our parent and we're going to write that one out. That's when we use the -2, -1, 0, 1, and 2. Do not try and do it in your head from the parent table. I've seen a lot of people just try and draw the x plus h, y a plus k, and not write down the parent table first. It is a very easy way to make a simple mistake. Oh, there we go. So then we're going to do our transform table. X plus h. Y times a plus k. So our h is 2. We're going to take all of our x values from our parent function and add 2. -2 plus 2. -1 plus 2. 0 plus 2. 1 plus 2 is 3. And 2 plus 2 is 4. We're going to take our y values and do y times a plus k. 2 times -1 is -2. -2 plus 1 is -1. And we're going to take this one. 1 times -1 is -1 plus 1 is 0. And when in doubt, put them in a calculator. Like, y'all love to use calculators. It's all good. 0 times -1 is 0. Plus 1 is 1. 1 times -1 is -1 plus 1 gives me 0. And our last one is going to be -1. So we get a bunch of points. We're going to plot our points. 0, -1. 1, 0. 2, 1. 3, 0. 4, -1. Again, absolute value. You will use a ruler. I just can't because my iPad's a jerk. Ruler, 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 ruler. Do not freehand a line. Okay, any questions on the absolute value? It's a little kooky. Okay, I think this is probably the hardest one on here, the piecewise function. Oh, and I love it, my squiggle's in the way of the minus sign, but that's okay. So what we have is 2 lines, which means I'm going to wind up making 2 tables. Because I think that's the easiest way to do it, is I'm going to take my top line here. I'll do this one in black. We pick x's to find y's. And my rule here is that my x has to be less than 2. I need to know what's happening at 2. But all my x's other than that need to be smaller. So what are some numbers smaller than 2? 1, 0, -1. You can do more. Yeah, you can do whichever ones you want. I'm just going to do those 3 because it's a line. It's pretty simple. So we're going to evaluate what happens. 2 in place of the x. -2 times 2 is -4 plus 4 Nope, negative 4 plus 4. 0. There we go. Just be careful. So x of 1, negative 2 times 1 is negative 2. Negative 2 plus 4, 2. 0, negative 2 times 0, plus 4, 4. So I'm going to plot my points. I've got my 0, 4 up here, 1, 2. And then before I plot that 2, 0, I'm going to remember this can be really, really close to 2, but it can't quite equal 2. So when I plot that 2, 0, I'm going to put that open circle. Because it cannot equal 2, but it could equal 1.9. 1.999999999. Well, it's green, but that's okay. And we're going to put our little line segment going this way. Okay, and we're going to do that same process for the other side. I'm going to make another table. We're going to pick x's to find y's. This time, though, my x's have to be greater than or equal to 2. So we know we need to know what happens at 2. What are some numbers greater than 2? 3, 4, etc. So we're going to substitute them in. 2 minus 3. Negative 1. 3 minus 3. 0. 4 minus 3. 1. So we're going to have our 2, negative 1 down here. Since this one does have the equals 2, we can do a regular dot. 3, 0, and 4, 1. Bless you. Yeah, we're going to look at 7 in a second. I'm going to look at 7 in a second because that was a lot. That was a lot. Yes, dear. We came up with these numbers because for that one, my x's had to be less than 2. So I always want to know what's happening at that endpoint, so I'm going to include the 2, even though I know it's an open circle. And then anything smaller than. Correct. So that rule, all it is how we pick our x's in our table. Other than that, it's just a regular line. Okay? Then we're plugging the x's into the equation. My minus 2x plus 4, or my x minus 3. We take our x's that we picked using our rule, and we substitute them in. Like this one was, I picked this 2 because it was my end unit. I wanted to know what happened there. 2 minus 3. Taking my minus 1. Okay. Cool, cool. I heard a request for 7. The domain and range one right below this. So is this continuous or not continuous? Not continuous. What kind of function is this? It's a step function. This is what a step function looks like, where it's just horizontal steps right there. I know mine's in colors and yours is in black and white, but that's okay. I'm actually going to start with the range because I think the range is easier to see on this one. What values do we have in the y's? And nothing in between, right? 4, 6, 8, and 10. Nothing in between. So this is when we're going to use the squiggly bracket, and we're just going to list them out. 4, 6, 8, 10. It's those values and those values only, not things in between. So I can't say it's between 4 and 10 because there's nothing here that's going to have a value of 5. There's nothing here that has a value of 4.5. It's just 4, and then 6, and then 8. How about our domain? What do we see there? Yeah, we have a lot more options, right? So you have one of the options, and one of the ways we talked about it would be to come in here and write it for each individual segment. That is absolutely an option. It's a long way, though. Because what is the very, very smallest place we have a dot? What's the smallest X I've got? There's nothing less than 1? 0. So the very, very smallest place I have a dot is there. What is the very, very biggest place we have a dot? 12. So we know my x's are between 0 and 12. Can it equal 0 and have a valid answer? How can we tell no? The hole, the open circle. It doesn't work when there's been a hole stabbed in my line. So we know that that has to be greater than 0. It could be 0.00000000001. That's bigger than 0. It just can't be 0. How about my 12? Can it be 12? Yeah, because we have that filled in circle. So it cannot equal 0, but it can equal 12. That's kind of the easier way to write this. I'm absolutely okay if you do from 0 to 1, 1 to 2, 2 to 3, and 4 to 12. Yeah, right here. And then there's a set over there as well. Okay. So that's all of that page. That leaves you pretty much just that second page to work on. We have 4 minutes until announcements. So it gets you down to mostly just this page, which we did one like this on our chapter review the last time. We've done an end behavior today, and we've identified transformations today. So that little table is the only thing we didn't do today, but we have done that together before. Okay, so you've got about 3 minutes until announcements are about to start. I will post the answer key for the review guide today. Might not be till 4th period, or 5th period, just because I don't know if I'll have time. But I will get this video posted as quickly as I can. Okay?